Hey guys, welcome to the calculus lesson on concavity. So you kind of already know what concavity is. It's basically when the curve is facing up, so this first one on your left, or when the curve is facing down, the second one on the right. So the first one is concave up because the curve is facing up. The second one is concave down because the curve is facing down. So these are pretty easy to recognize when you have the graph, or you are allowed to graph it. But it's kind of difficult to do so when you have an equation and you can't easily graph it and figure out which it is. So that's where derivatives come into play. So how can we use first and second derivatives to solve for these? Well, we just have to analyze it a little bit closer. So for concave up, the second derivative has to be increasing. Why? Well, the second derivative is basically the rate of change, or the slope. So whatever the slope is of the original graph, that is what the first derivative is going to say. So if you notice here, it's a very steep slope at the start, and it's negative. Then you get so that's going to be like a negative 99 or something, where the slope is really steep. Then you get somewhere here, and it's not as steep of a slope. That's going to be something like, I don't know, negative 20. And then you get to here, it's 0 at that point. And then it gets increasing, so like negative 20, positive 99, or positive 20, positive 99. And it's increasing. You go from that negative, really big number to a smaller negative number, increasing to 0, to a bigger positive number, to a huge positive number. So that's always increasing. So when it's concave up, the first derivative has to be increasing. Let's not make this a plus, actually. Let's do a little up arrow for increasing. Now for the concave down, it's the opposite. You go from a super positive, super steep slope, positives, less steep slope, 0, negative, less steep slope, negative, super steep slope. So that's decreasing. When it's decreasing, that means this first derivative is decreasing. We can also use the second derivative, though, because the second derivative is kind of like the slope of the first derivative, right? If the first derivative was its own function and you took the derivative of that, then it's going to just be the slope. So you can kind of apply that. So if f of x is increasing, then that means the slope is positive. If the slope is positive, then that second derivative is going to be positive. And then for concave down, if the first derivative is decreasing, that means the slope is negative. And if the slope is negative, the second derivative is negative. So this is kind of how you can solve for each of these. Obviously for, if you have the first one, if you have just the original function, you can see when it changes from decreasing to increasing, and when it hits 0. And then for concave down, when it changes from increasing to decreasing, and when it hits 0. But it's easier to look at the whole function and just take the derivative and figure out if it's increasing or decreasing, or take the second derivative and then just see if it's positive or negative when you plug in a point. So there is an important term here, and it's called the inflection point. So an inflection point is where the function changes concavity. In order for the point to be an inflection point, the point has to lie, in the domain of f of x. Possible inflection points are where the second derivative equals 0 or undefined. So when these guys change signs, because if they're continuous and differentiable, and they change signs, that means they have to hit 0. That is the point where concavity changes. So a graph can look like this, where you have it like this. Oh, that's awful. And that's f of x. And it changes concavity right there. And then when you have your first derivative, and it changes concavity, well, let's look. You can't really tell as easily, but your first derivative, this is going to be negative, so it's underneath negative. And then at this point it hits 0, then it goes positive, 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 and then it goes down, hits 0, negative, negative, negative. That's an awful graph. And then when you get to f prime of x, or f double prime of x, the way you can tell, by the way, with the first derivative is when it changes directions. So when it changes from increasing to decreasing. So since it changes from increasing to decreasing here, we're going to pretend that is exactly where the point on f of x is. That's when concavity changes. And then for f double prime of x, if it changes from positive to negative, since it's concave up, it's going to be positive, and then it changes to negative when it's concave down. That is the inflection point. So, how can we use these? Well, let's take a look at an example problem as I erase this. So, an example problem looking at the concavity of a function. That function is going to be x cubed, so f of x is equal to x, not cubed, to the fourth, minus 4x cubed. So we can take the derivatives here. So f prime of x is equal to, you can probably do this one in your head, 4x cubed minus 4 times 3, so 12x squared. And then you take the derivative of that, so the second derivative, and that's going to be 12x squared minus 24, that is a 4, 24x. And then you can differentiate, you can factor out. So 0, because we want it to be equal to 0, 12x can be factored out. That parentheses is facing the wrong way. And then you're left with x minus 2. And so that means x is equal to 0 and 2. But wait, we have to check this. We have to make sure this is correct. And so to check it, you can draw a little number line. So 0 and 2. And things in between are anything bigger or smaller than each of those numbers. So we have to plug it in to the original equation. We don't plug it into the original equation. We plug it in to the second derivative. So when we have -1, that's going to be positive because you have 12 times -1, so that's -12, times -1 minus 2, which is -3. So that's going to be positive 36. So that's a positive number. Then when you have 1, that's going to be a negative number because 12 times 1 is 12. And 1 minus 2 is -1. So -1 times 12 is -12. This middle part is going to be a negative number. And then 3, you can plug it in, but 12 times 3 is a positive 36. 3 minus 2 is 1. 1 times 36 is 36. So that's a positive number. So now we're sure that our points of inflection are at 0 and 2. So we would denote that by finding the actual point. So you can go ahead and plug it in to the original function, 0 and 2, to the original function to find the points. I'll actually give you guys a couple minutes to do that. Okay, so hopefully you've plugged them both in and found that the points are 0, 0, and 2, negative 16. And that's it. That's how you solve for concavity.